Okay, welcome to INDS 3050, Introduction to Metals Processes. This is the first lecture on metal properties. So, learn how to use the software, we'll see how it goes. So here's the title page. And so why do we make things out of metals? Well, they have special properties that other materials don't have in some cases. So one thing is they conduct heat and electricity. So we can make electrical wire, radiators, cooling fins on radiators, things like that. So it conducts electricity and heat because of the atomic structure of it, and that there are electron clouds. And it's easy to transmit electricity because electron comes in and then it knocks one out the backside, and it conducts electricity very well then. It can also be very strong. So we make bridges and pipe and structures out of it, buildings, because it can be strong. Not always, but if the right materials are desired and the right processes are done to produce that, then we can have a strong structure. Another thing is we can make it hard or soft by heating it and cooling it. There's several different ways of hardening the material. And you can make steel, let's say, just about as hard as, almost as hard as glass. So fully hardened steel can almost scratch glass. But what's interesting is you can actually take and make a die out of the same steel that you're cutting. So you could have one of them in the softened condition and one of them in the hardened condition, and then that die will actually cut whatever that piece is. Okay, so chemical production, such as chemical properties. So things like food processing. We live in Wisconsin, most of us, and in Wisconsin and the areas around it, much of the food and milk that's produced is handled in stainless steel. And so stainless steel, we'll talk about that later on, what makes it stainless and everything, but it is corrosion resistant. Also, corrosion resistant at high temperatures. That can sometimes be a different thing. So some stainless steels are corrosion resistant at high temperatures, other ones are not. And turbine engines will not go any faster, in other words, a jet engine in an airplane, unless you get the ability to withstand higher temperatures. So as we go to higher temperatures in a turbine engine, the efficiency gets higher. And then finally, bells, jewelry, things that look nice, and metal is beautiful. Okay, generally there's three types of properties: chemical, physical, and mechanical. So the chemical properties we talked about in the last slide a little bit, that has to do with these resistance to corrosion and things like that. The chemical properties are specific to the makeup of the metal. It could be alloyed with different alloys, different metals, and that will produce sometimes a really corrosion-resistant alloy, or it may produce something that's not corrosion-resistant in the particular environment you're interested in. Physical properties are things that you can't really change, like color, density, electrical and heat conductivity, and a few other things like resistance, things like that, magnetic properties. Mechanical properties are what most people are after. Hardness, hardenability, ductility, machinability, weldability, strength. These are all properties that we're going to talk about in the next few slides. Okay, the first mechanical property we're going to talk about is hardness. And hardness is a measure of the ability to resist penetration. And what we mean by that is to take a dent or to deform permanently. Okay, so hardness is the measurement of that. Hardenability is the next thing that we want to talk about. Now, hardenability is usually required or referred to as the ability to be hardened by heat treatment. Most metals can be, if they're ductile, they can be hardened by cold working, but typically that doesn't change the hardness all that much. So hardenability is the ability to be hardened by heat treatment. Brittleness is a tendency to fracture with little or no bending. Typically, brittleness is the lack of the following terms. So we don't really have a brittleness test, but we have a ductility test or toughness test. So ductility is the ability of a material to be deformed in tension and compression without fracture. Now, this is very important because some materials can be deformed in compression, but not very well in tension. They'll pull apart. So malleability is the ability to be deformed by compression or hammering, typically, is how that's worded. Okay, I'm going to give some examples here now on this next slide. Toughness is the ability to withstand a sudden shock without breaking. So an example of this would be, well, if you have a hammer or something like that, it would be very tough in order to not shatter when you hit something else with it. You'd like it to be hard and tough, but typically these are at odds with each other. Toughness and hardness typically are opposites. So as I increase the toughness of a metal, and you can do that in most metals, it would typically decrease the hardness and some of the other properties that we'll talk about. Okay, machinability is how much energy or how easy is it to cut the material by a machine tool. So some other harder material. Could be anything from diamond to hardened steel. And then weldability is the ability of molten metal to join together. So some materials are not very weldable, and therefore an example might be cast iron. If anyone ever broke an engine block or something like that, and you try to weld together, if you don't know what you're doing, you can definitely just continue that crack further along. In this next section, we talk about mechanical properties. Mechanical properties are very interesting, but they're also more complicated than some of the other properties we talked about so far. We'll actually have to use some math in this. So the four different properties are tensile strength, the ability to resist pulling apart. So that's like pulling on a string or a rope or something like that. And we'll do a demo with that in 1 second here. Compressive strength is the resistance being squeezed or compressed, pushed together. So if you push something together, if I take this spool here and I push on both ends, it's in compression, okay? Trying to squeeze it together. Shear is like scissors. We're pushing on one surface relative to another surface. So exactly, that's why they call them shears, is because it's putting that material in shear. Example of this might be a rivet, where you have one section of a plate pulling in one direction and one section pulling in the other direction, and that rivet between them is going to be in shear. It's going to try to slice it. Okay, and the last one is torsional strength, is where we're twisting something. Could be like a crankshaft in a car engine, or axle, or a drive shaft, or something like that, where we're trying to spin something and something's resisting it. Okay, so we have tensile, compressive, shear, and torsion. Okay, this subject is a little bit stressful. Bad joke. But stress is equal to the load over the area. Okay, so you have to know a little bit of math, a little bit of geometry here. The area is the cross-sectional area. So this is a little bit confusing, but I'm going to explain that now with a little demo. So if we were to take a, let's see, a really small diameter wire. Now I have a piece of wire right here. It's hard to even see, but that is 5/1000ths of an inch in diameter. It's about the same diameter as your hair. I'm going to wrap that around both of my fingers here. Okay. And I'm going to put about 10 pounds of force on here, maybe 15. Now it's not calibrated. This is a very, and you can see that I can actually snap a piece of, that's a stainless steel wire. Okay. So it only took about 8 or 10 pounds to break that, let's say. Okay. If I take a slightly bigger diameter wire, yeah, this is somewhere around 20/1000ths of an inch, something like that, 22/1000ths, and I put it between a couple of, get this going here, a couple of needle nose pliers. I'm not sure if, I haven't tried this yet, so let's see if it works. And I pull really hard on this. I can also break that. But it took a lot more force. I don't know if you noticed it kind of stretched a little bit. If I would have stretched it and then let it go back. Also, you notice, that's hard, you can't see it on here, but it's actually smaller in diameter at the end a little bit. So now we took 2 wires of kind of the same strength, and we pulled on them till they broke. Okay, and the one that had more atoms across the cross section, that actually had more strength. Now here's another example here. This is a, I don't know, 3/16 of an inch in diameter rod. Same material. Looks a little bit different, but it is steel, even though it's copper coated. If I were to pull on this as hard as I can't break it. I'm stretching it. I'm actually making it longer. If I pull on this, I'm making it longer, but I'm not making it longer permanently. I can bend this bar and it goes back to its original position because I didn't exceed some limit. Okay, so in the first 2 examples, I exceeded a limit. In the third example, I'm not strong enough to do this. Okay, so what's going on here? The deal is, as I'm pulling on this, remember that the atoms are bonded together with kind of a atomic bond that's got a little electron cloud around it, but essentially, as I'm pulling on it, these atoms are getting slightly farther apart. And the other thing is, when I slice this way, you can imagine there's a lot more atoms, they're very small, there's a lot more of them across that cross-section than there are in the other 2. So the deal is that you have more atomic bonds across this bar than you do in the other 2 bars. Therefore, it's going to take a lot more force in order to break it. So that same theory then we could apply to some sort of measurements and some math. Okay, so I'm going to put that back up. So stress is equal to the load over the cross-sectional area, and that's the reason of it, because if I put 10 pounds on that small diameter wire, it breaks. If I put 10 pounds on that slightly larger diameter wire, it stretches a little bit and goes back to its original position if I would have done that. But if I put a little bit more, it actually breaks. And again, the bigger bar would not break even. It would stretch measurably. Even when I was just pulling on it, it would stretch measurably if we had the right measuring device. Okay, what kind of units do we have? Pounds per square inch. Now, remember that inches can be represented by little quote marks next to something, or IN, okay? And I use those interchangeably. Also known as pounds per square inch, or PSI, okay? Now, I don't like the term PSI because it doesn't really tell you what's going on. It's pounds per square unit. So there should be a little slash in between these things on the PSI. But as long as you know what it is, then you're fine. A Newton per square meter, a Pascal, you're not probably quite as familiar with. But a Newton per square meter is a pretty small unit. Now let's think about this. A pound, I'm going to put me back up here so I can use my hands. A pound, okay, you know what a pound weighs, a pound a meter or something like that. On a square inch, now a square inch is something like that. So a pound weight on a square inch, that's a fair amount of force, okay? Let's think about a Newton. Now a Newton is somewhere, we can't use kilograms because it's not a force. A Newton is about a quarter of a pound. So think about a hamburger, okay? It's about a quarter of a pound. A Newton's a hamburger. And we're putting it on 1 square meter. Now that's really big, 1 square meter, okay? Yeah, a manhole cover, let's say, is just under a square meter, okay? So a hamburger sitting on a manhole cover, distribute that load over that manhole cover, that's a really low force. So when you look at pascals, you tend to see really large numbers, even though they represent the same thing as, let's say, pounds per square inch. So let's go back to our, okay, so we're going to take a wire that is 0.2 inches in diameter. Now, that wire I just showed you, the biggest one I showed you, is right around there, okay? So if I took that big rod, as I say, call it a rod, and I put 1,000 pounds on it, okay? What's going to happen? Okay, well, we need to figure out how much stress is on that. In other words, each material has a maximum amount of stress that you can have before it pulls apart into 2 pieces, okay? So if you exceed a certain number, you will have 2 pieces. Or you may have stretched the bolt or whatever the part is, and now it's deformed and it can't be used anymore. Okay, so let's look at this. We have a 0.2 inch diameter, inches in diameter rod. We know the area of this rod is, okay, so you may have seen it pi r squared. Trust me, pi over 4 times the diameter squared is the same as pi r squared, except we don't have to keep on changing diameter, radius, and stuff like that. So if you haven't used this equation before, kind of memorize that or remember it, okay? So if we substitute into this equation, we have a 3.1415 over 4 is 0.78, something like that, times 0.2, and we get, a number of 0.0314 inches squared. Okay, so if we want to find the stress on that, it's pounds per square inch. Just remember that it's load over area. And so we have 1,000 pounds over 0.0314 inches squared. I should have had the units on that. And we get 31,000 pounds per square inch. Now, that rod that I showed you is actually steel. And that steel rod probably would have a strength in the neighborhood of a minimum of 60,000 pounds per square inch. So we're about half of what it would take to start to deform that rod permanently. Okay? So that's reasonable. Okay? So strain. What is strain? Now, when I pulled on the first 2 wires, you probably saw them elongate slightly before they broke. Okay? So the strain is the change in length of a rod or bar or whatever it is. The problem is that because let's see, every one of those bonds, I'm going to put it back on the thing here. So if I start pulling on a wire, every one of the atoms in those things, let's say this is a string of atoms, right? If I pull on a really long bar, all those bonds stretch slightly, so that really long bar will stretch a fair amount, okay? If I pull on a really short bar, it will only stretch a little bit. So the length of the bar that you're stretching actually matters. And so we need to normalize that. What that means is we need to bring it within the realm of, okay, so if it's 12 inches long and it elongates some distance, if it was 1 inch long, it would elongate that. So let's figure that one out. Okay, so we'll go back and look at that. So the equation is the change in length, or the final length versus minus the original length over the original length, okay, is strain. So that means that if it elongates a few thousandths of an inch over 1 inch, well, the strain is, let's say it's 3 thousandths. It'd be 3 thousandths of an inch per inch. Now, the crazy thing is, if you have inches over inches or millimeters over millimeters, the units cancel out. But I like to say inches per inch because it reminds me of what it actually is doing. So let's do an example problem here. We have a rod that's 6 inches long, and when we elongate it, it elongates to 6.006 inches. So 6 thousandths of an inch, it increases in length. Notice I'm using the quote marks here instead of inches. Just get used to that. We'll use those interchangeably. It's easier to do the quotes than the inches. Okay, so here's our equation. Again, we substitute in the equation. So 6 thousandths, 6.006 minus 6 over 6. So 1 thousandths of an inch per inch is what the elongation is. So what does this all mean? Why are we using this? So the next diagram we're going to look at is actually a graph. Stress versus strain. Okay, so that means that stress is on the y-axis and strain is on the x-axis. You put the y-axis, the independent variable versus the dependent variable, which is on the x-axis. Okay, so stress is equal to force over area. So now, let's say we plot what we just found a second ago. We found that it was 31,000 pounds per square inch. So on this axis, we go here to 31,000 pounds. Let's say it's right here, okay? And on the strain, it was 1 thousandth of an inch. So that this strain here is going to be really small numbers. So let's say 1 thousandth of an inch is somewhere like here. Now what I told you is it was about half the distance before it actually started to fail. Okay, so it was 31,000 and the strength is 60,000. So it would be right about here on this graph. We would have this point, okay? And if I put 2,000 pounds on it, well, we'd be right up here, right about where it's going to break, okay? Now, what happens is, with metals, if it's a brittle material, it's going to load to this point and it's just going to fracture. We're not going to have any elongation where it like gives us a warning. Now we know that if we have a rod or a bolt or something like that, even the stainless steel here, I don't know if I can pull it again, but if I take a piece of this and I gotta get it around my fingers. I don't know if I can. That's too slippery. If I pull on it, it actually gets a little bit longer right before it fails, and then it's slipping in my fingers. Anyway, and then it fails. Okay, so what happens is you get like a warning, and that's the nice thing about metals. It's not like a ceramic where like I'm bending it, all of a sudden it breaks, and you have no warning. Okay, so you want that warning because let's say, I don't know, I have a component like, I don't know, some sort of hook that's holding me up when I'm rock climbing. And you see that hook is starting to bend open. Well, that's where you want to somehow get that load off that hook before it breaks. If you hit a curb with your car, it's much better that the wheel doesn't go rolling down the highway than if your suspension kind of bends, and it's not great, but at least it's not in two pieces. Okay? So that's called yielding or ductility. There's a lot of terms for it, but essentially, when the metal yields, it will not go back to its original dimension. Okay? So there are two ways metal will elongate. One is elastically, where we just stretch those bonds and it'll always go back to its. So a spring is something that has elastic deformation. Okay? And plastic deformation is where it deforms permanently and doesn't go back to its original dimension. So if we go back to this drawing, this first part you can see is linear. It's like a spring. I pull 31,000 pounds on it, and it elongates 1,000. I pull 60,000 pounds on it, and it's about 2/1000ths of an inch that it elongates. Okay? And then if I pull past that, what happens is it starts to elongate without much of an increase in the actual stress level. In other words, I'm not putting a lot more force on it, but it is getting longer. And what's going on here, it's cold working a little bit, and it's getting smaller in diameter. As you stretch the thing out, it gets smaller in diameter. So theoretically, we should actually have to recalculate this whole stress thing. But because we're kind of lazy and we're just trying to get an idea of what's going on, we don't do that. So the metal looks like it's getting stronger for a while, and then it's getting weaker. It's always cold working, but what's happening here is the diameter is getting so small that it eventually breaks. Okay, so the stress strain diagram, we can load it all day long, up and down here. It's linear, more or less, and it just goes up and down. Okay, once I go past a certain yield point, then it starts to elongate more than it should. And if I unloaded it right now, it would go down to right about here. The elastic material, it would have the same slope. The elastic relaxation, it'll be the same slope as this going up. It would just make a big box here. Boop. And then if we want to load it again, it would go up to here and then continue along this path. Okay? So if I'm an engineer and I'm building a bridge and I get past this yield point, what do you think is going to happen? My bridge now is sagging in the middle, and it will never go back to its original dimensions. The bridge is done. Okay? You drove something over too heavy, and the bridge needs to be replaced. That's a bummer. Oops, sorry. So we're going to define some of these points on this diagram. So one other thing I want to point out to you, and they kind of say something about it here, but I'll give you an actual equation in a minute, is that the slope of this line is important. The slope of this line tells its stiffness or its elastic modulus. So if I were to take a piece of aluminum and this was a piece of steel, the aluminum would elongate kind of more like in this direction because it stretches a lot more under the same load. It might be the same strength if it's a certain kind of aluminum. Like a high strength aluminum would have the same strength, let's say, as a lower strength steel, but it will elongate a lot more under that same load. Okay, so it's got a lower modulus of elasticity. Just give you some numbers. Let's say steel is 30 million and aluminum is 10 million. So about 1/3 of that of steel. Okay. Okay, so it's a little bit hard to read this, but the Young's modulus, otherwise known as the modulus of elasticity, is equal to the slope, which is equal to the rise over the run. Okay? All that's saying is it's the change in the stress versus the change in the strain. Okay? So the units on that, because the strain is unitless and stress is pounds per square inch or newtons per square meter, is going to be the same. So weirdly, stress is pounds per square inch, and so is the modulus, because there's no units of strain. Okay, so what happens is we load this piece of material. Now this is what happens in steel. We get this little bump here. And this is due to a phenomenon. It has to do with other atoms being like oxygen and things like that, being stuck between the atoms. Once the metal gets to a certain yield point, it drops down a little bit, and then it starts to work hard and goes up. This is just a phenomenon that happens in steel and maybe a couple other alloys or elements. Okay, so we get strain hardening or cold working or work hardening, all the same thing. Then we get necking. Necking is the cross-sectional decreasing in area. And then we get failure, okay? So this is a ductile material. Again, a brittle material would just go up on this linear deal, and then you just see it break right here, okay? So those are two representations of a stress versus strain diagram. Please take note of this, take some notes, and do a sample calculation. I should be able to add one here to this presentation here. Okay, so the elastic modulus, if we want to solve for that, also called the Young's modulus or modulus elasticity. Okay, these look like scary letters. Greek looks like Greek to me, but remember that all this is the elastic modulus is equal to stress, which we know what that is now, versus over strain. Okay, and what is stress? Or the change in stress over the change in strain. Okay, and so that is stress 2 minus stress 1. Now, if you pick 2 points on that graph, you'll see that we did a calculation at 31,000 pounds per square inch. And then if we pick 0 as the other point, it makes it easy, right? So 31,000 pounds per square inch minus 0, that's 31,000. And then here we have, well, there's not, shouldn't be a minus sign here. Here we have strain as 1,000th of an inch per inch minus, again, 0 on the graph. So change in the rise over change, or, rise over the run. Sorry, a little confusing. Okay, so we crunched the numbers, and I don't know if you remember, I said that steel has an elastic modulus somewhere around 30 million psi. And again, and so this must have been something like a piece of steel, because that's the modulus. Okay. Now we could do the same thing with pascals, and hopefully achieve the same answer. There's a conversion you could do. Obviously on the internet you can go and get something like that, but there's a if you do units canceling, you can figure out a conversion for pounds per square inch versus the pascals. So that was a big hiatus we took there to figure out how to put some math onto the stress and strain and mechanical properties. And some of these other properties also have math associated with them, but I think the one that I just went through is the most important, because it kind of describes how metals behave, whether it's ductile or whether it's brittle. So a ductile material would have, so a ductile material would have this long tail at the end of the stress strain diagram, whereas a brittle material, again, is going to break right down there. Okay. So, elasticity is the ability to return to its normal size after loading. In other words, that first part of the diagram is the elastic portion where it's proportional. And essentially that's what a spring is. You use a spring in that elastic. If you ever did the spring constant when you were in the maybe physics class or something like that, you already did this. You actually already did Young's modulus. You just didn't know what you're doing with it. Now the thing with a spring is a coil, right? So we coil this thing around, and then when we pull on it, you just make a longer bar, okay? So it elongates more over that, you're taking a long bar and shrinking it down to a shorter distance so that when they pull on the ends of it, it elongates more. So a spring allows you to compress, and then it should go back to its original dimension. Springs can be made on the hard side where they'll crack instead of permanently deforming, or they can be made a little bit on the soft side. You want them somewhere in between, but you don't always get it right. So sometimes your car springs might actually crack. I had my Subaru spring, the top part of it broke off. And then my Defender over, 22 years, going off-road in Africa, the springs got a little bit shorter, so I had to put new springs in my truck. Okay, so the elastic limit is on that diagram, also called the yield strength. It's basically where that linear portion ends, and we no longer get elastic deformation. A mechanical engineer will design up to this elastic limit. Now, they usually don't want to get too close to it, because if someone does something stupid, then, like drive something too big across a bridge or something like that, it could fail. So what they do is they use a safety factor, maybe 2, maybe 10, so that the bridge or whatever that structure is stronger than it needs to be. Okay. Plastic deformation is that permanent deformation that happens after you exceed the elastic limit. So you should, study up on these terms a little bit. You for sure will see them again. Okay, fatigue. Hopefully you're not feeling too much fatigue right now listening to this, but is a failure caused by a alternating stress. Something that happens over and over and over again. So metals can fail if you just bend them back and forth and back and forth. I don't know if you've ever done this with a paper clip, but if you take a paper clip and you bend it back and forth enough times, see if I can find one. So I have a paper clip here, and if I open this thing up, and this is kind of a thicker one, so it's going to be a challenge. Okay, so I'm going to take this and I'm going to bend it back and forth right in the same spot. Now what's going on there is we exceeded the yield strength of that material, right? And as I bend it back and forth, it starts to get harder and eventually it fails. The other thing you would notice, if you feel it on your lip or something like that that's sensitive, it's a lot hotter than it was a couple seconds ago. So there's something going on here. It got stronger, kind of. It was harder to do, and it got hot, and eventually it broke. So that is not really fatigue. That is ductility and all that kind of stuff. But if I take this same paper clip and I just bend it slightly in the elastic zone, and I keep on doing this a couple million times, the same thing will happen. Okay? Why? Because what happens is it forms a little crack on the surface. And that crack is a stress concentration. In fact, there is little cracks on the surface of this somewhere. I could feel them. There's little like bumps on the surface of this. And it probably failed on one of those bumps when I was bending it back and forth. So as you bend this thing back and forth, even if you're in the elastic zone, if I just take this and keep on bending this little end here, if I do that millions of times, it can actually fail that way as well. An example of this would be a bicycle. The sprocket on a bicycle, or the actual pedals, are connected to an arm, or the actual bottom bracket. All of these things are subject to fatigue because they go around and around, and you're loading it one way, then you're loading it the other way. You're loading it one way, and you're loading it the other way. Bikes tend to fail right at that bottom bracket, right where the bearing goes through. There's a weld along the bottom of that usually fails. Aluminum is more susceptible to fatigue than steel, let's say. Airplanes are made out of aluminum, and what happens is after a certain number of times the airplane takes off, the wings flex up, and they come back down. It goes over bumps as you're going along, and those wings are flexing. They can only do that so many times, and then they have to replace parts of that airplane or retire it. There's been instances where whole parts of airplanes ripped off before they had really good ways of determining this. Airplanes have pretty much only been flying commercially, aluminum ones, after World War II. So when they started making jets, somewhere around 1970s, they flew them for a long period of time, and eventually some of them started failing. Okay, so let's go back to... So fatigue is failure that's caused by a stress that's much below the elastic limit of the material, but over a huge number of cycles. Okay, so there's generally, this is kind of funny, iron is so important that we classify materials as ferrous, I mean based with iron, or non-ferrous, which is everything else. So it's kind of funny, although nowadays there's lots more alloys out there, but we're still in the Iron Age. Iron is still used as the primary metal in steel. If you look at a car, things are changing a little bit. They're putting aluminum in cars. It's not always because it's better, though. Sometimes it's because, I don't know, the mechanical engineer heard that aluminum is a lighter material, so they want to do that. I'll give you an example. There is, let's say, an unnamed tractor company that was producing a part. I was reviewing a paper from one of the a student getting his PhD and going back to school through the University of Wisconsin-Madison, and I reviewed some of these papers. And there's a big arm. I'm not an ag person, but there's a big arm that unloads, I think it's corn, from one vehicle to the other. And the arm has a hinge in it, okay? And that hinge right now is made out of ductile iron, okay? And we'll talk about the different kinds of iron, but it's basically ferrous. And the engineer heard that it was lighter to make that out of aluminum, because aluminum's a lot lighter, right? So he ended up designing it in that other material. And I just told you a few minutes ago that the stiffness, or the elastic modulus of aluminum, is less than that of steel. It's about a third that. So you have to use more of that material. Even though it's about a third the density, you have to use a lot more of it. Okay, aluminum's expensive. The other thing is, when you put aluminum up in contact with something that is iron, there's like a battery that actually forms there. When you get a liquid in there, like rain, it starts to corrode. It's called galvanic corrosion. And you've probably seen this. If you ever try to get the rims off the rims get mounted to your brake disc, brake rotor typically. So your brake rotor is there, you got studs, and then you have this sometimes aluminum wheel. I like steel ones better, but aluminum wheel up against that cast iron rotor. And over time, if there's salt and water, corrosion, you can't get that off. I've actually seen a student, I had to give him a sledgehammer to get that off because they've corroded together. So putting two dissimilar materials together is a problem. And in this application, this person was designing, in order to do that, they had to put actually little plastic bushings in there or whatever to try to keep it from. So it also wasn't as stiff. So the arm, they had to make a, I I don't know, they had to do all kinds of stuff to make this, just to take a piece of ductile iron and make it into aluminum. Now, can we increase the strength of the ductile iron? Yes, you can. All you have to do is heat treat it. And I'll talk about that later. There's a special heat treatment you can do to ductile iron that can pretty much double the mechanical properties. So, going back to this slide. So, a pure metal usually doesn't have much strength, so you need to kind of alloy the iron or whatever it is with something else in order to get the properties you want. An alloy is a mixture of two or more metals with other elements. Sometimes the elements don't have to be a metal. They could be an element such as carbon, and even gases can be an alloying element. Parts per million of oxygen in titanium will strengthen it significantly. It'll also make it really brittle. So you have to be really careful when you process titanium that you don't have even small amounts of oxygen in there. Also, nitrogen in many alloys is the same thing, even in steel. So ferrous is iron-based, and non-ferrous is all the other alloys. Okay, and that is the end of this presentation. Thank you for listening. Hopefully you study this. I may try to put some quiz questions in the middle of it. Hopefully you enjoyed those, and go over those problems again, understand that, and stress strain diagrams are pretty important to metals. So over and out for now, and we'll see you next lecture.